Hello, my name is Andrew Weed. I'm a surveying and mapping student at East Tennessee State University. I'm going to talk to you today about orthophotos and how we obtain them here, specifically where I work, and how we actually bring them into a CAD environment and use them to actually create a deliverable that's in the right place and at the right scale. So I'm going to share my screen here. Now, this is just one of many projects that we have. And this particular project, I flew with a DJI Phantom 4 RTK. And this right here is Newark International Airport, just across the river from New York City. So, as you can see, this is runway 22 left. Our actual project site is just off that runway approach. I believe it's right up here. It's just up here on the north side of Route 1. Yep, so this is our project site, and we actually ended up building a new warehouse facility, my particular construction company. We utilize low-level aerial drone photogrammetry to help us with earthwork quantities and as-built mapping so that we can verify that the site was built in substantial compliance. We obtain the, aerial photogrammetry with a low-level drone flight, but then we actually offload it to an online service that stitches all the photos together based on the ground control that we provide and creates an orthophoto. Now we know an orthophoto is an actual planimetrically rectified photo, basically a stitching together of all the photos so that it, reduces distortion and tilt and, accounts for scale so you get one complete package. That's what we work with. We work with orthophotos because they've been fixed. So this is the actual project site, and we have ground control that we provided to the mapping service so that they could, after they stitched the photos together, because we flew this with sufficient overlap. I think we had more than 60% end lap and side lap. And these are our aerial targets. You can actually see that it's a painted target if you zoom in close enough. See, so that's aerial target 4. And we also have actual GPS located points. These points themselves uh, actually collect GPS data so that they can actually rectify their location, which is good, especially if you have a site in the middle of nowhere and you don't necessarily have site coordinates, but you want it to be pretty close to the real world as you can get. This will actually get you in the ballpark. It's not survey grade, but it gets you in the ballpark. And plus, when you have a pair of them working together, see, we had actual 2 arrow points, it actually gets you that much closer. So we flew the site, we obtained all of these pictures. Every one of those blue dots is actually a camera position that the drone had. And this was a very low level flight. I think it was a little bit over 300 feet above AGL, above grade at the site. So it's very, very low level, very high resolution. And then once every single one of these photos is stitched together, we can actually download an orthophoto, and that's what we want. And I want to go over with you today how I check that the orthophoto is in the correct location and how to bring it into a CAD environment. And so you know it's in the correct place. In this case, every single one of these aerial targets, 5, 4, 1, 2, 3, and even these arrow points here are in our project coordinate system. We have all of our background mapping, all of our design plans, and everything lives in this place. So we want our as-built data and any drone data we collect to live in the same place. basically as the entire project. That way we're not drawing the as-built over in space and then trying to move it on to make sure everything's inside the property lines where it's supposed to be. So this is based on project coordinate systems. Now, they don't have to be any sort of state plane coordinate systems. These are just, a local grid. We could say that this intersection of road is 100 north by 100 east. It doesn't matter as long as you provide coordinates for these points. Once everything is stitched together and it's actually, we check that all of our residuals and the mapping actually conforms. In this case, all of our targets were, the image quality was good and our, root mean square of our error was actually very good. This actually looks bad because one of the points, they couldn't tell the elevation of it. This one right here. That's just because it was on top of an outlet structure, but that's okay. We know where that 3 feet is coming from. So the root mean square of the actual error is, good. And we know that the images are stitched together. And that's also not saying, hey, these points are that bad. It's saying, hey, when we stitched all these images together based on the drone's GPS geolocation, we had to move it a little bit, which is fine. That's why you actually provide ground control because the geolocation from the drone is similar to your cell phone. If you take a picture, it can actually, tell you where the picture was taken, when it was taken, and metadata. Very similar to most drones, at least most modern drones that I've seen. They, have a way to tell you, hey, I took this picture here at this time on this date, especially in this location, even this altitude or elevation. So we had all these images stick together, or we had them resolved together into an orthophoto, and every platform's different. You can actually resolve the photos yourself. Most modern programs like Trimble Business Center have the ability to, you can actually bring in all the photos and resolve them yourselves and do an orthophoto. We don't do that just because it's, more cost and time effective to have someone else do it. So we can download the orthophoto right here. And I'm just going to click to download it, but that takes a little while. I've already downloaded that. So actually that wasn't that bad. Now that you have the orthophoto downloaded, you can actually use it in a CAD environment. Now in Civil 3D, there's many ways to bring an image in. You've seen Professor bring in images just by, insert image and then place it randomly. When we're actually working with an orthophoto to map something and you actually want it in the project coordinate location, there's a different way to import the image that we do here that I'm going to go over with you now. And that different way actually uses the world file, which is this WLD file, which is just a basic text file. It's very similar to the one we worked with in Lab 3, I believe. It's just a very basic file, but this actually is instructions on where and how to place the image. These bigger coordinates here are actually, in this instance, this world file is formatted, but this is the top left pixel. And it's not the top left corner of the image, it's actually the top left center of the pixel. So the pixel is a square, and this is the center of that square right here. And that's the X coordinate, that's the Y coordinate. We're actually going to draw a point or a line to that coordinate value just so when we import the image, we can make sure that it came in the correct location. So I'm just going to go line and dot XY so that I can make sure I'm in the right place. And the X value is 593.13.1556605.209. Comma, my Y coordinate value is 693579.1000079652. And it's going to ask me for a Z value, but we don't really need an elevation. Okay. So I'm going to draw a circle just so I know which end we're looking at. So that should be very near the top left corner of the image that we're going to bring in. So this is the world file. It's just a very basic text file. So, and this is the top left center of the pixel. This is actually the X scale. So if you take that one pixel and the pixel measures whatever it does width by whatever it does height, this is telling it you need to make that pixel 0.02637 blah, blah, blah wide. This is actually the Y rotation. This is the X rotation. In this case, they're both the same. So we know it's rotated, you know, in the same. It's not rotated more in this way and stretched in that direction. This is actually the Y scale, and this is negative. I believe I'm honestly not sure, but I believe it's a negative because it's the top left of the image. So that scale is going down. If you think about it, you look at a plan from left to right or bottom to top, but this is going from top to bottom because we're in the top left, so it's a negative coordinate value. So this is the world file. Now, to bring in the image the way I'm going to show you here, you must have the JPEG and the world file. This is actually another version of a world file, but I believe this is the one that AutoCAD uses. And they have to be in the same folder as your image and have the exact same name. So this is the image. It's actually a rather large file. Yeah, it's 103 kilobytes. So we are going to bring this image in, not just by typing insert. We're going to actually bring it in by typing map I insert, which is another command that will actually look for the world file and place it in the correct location and at the correct size. So the command, and this is in Civil 3D, but I believe it works in plain AutoCAD as well. Map I insert. So you're typing I twice. And that brings up this insert image dialog box. Now, if we navigate to the correct folder, in this case, this is the Bridgeport 15E. 15E is actually the exit off the turnpike, anyone who's from the East Coast. That's the New Jersey Turnpike. It's very close to the airport, so everybody knows where that is. This is the image we want right here. And it just takes a second to load the thumbnail. And it's actually telling you the pixels. The width is 53,521 pixels wide by 41,080 pixels high. Yeah, this is a very high resolution orthophoto, which is nice because you can get, some really, really good detail. And you can, if you wanted to modify the where it's actually going, you could by this box, but if you don't, it's actually going to use the world file. See, now this, because I hit modify, it's actually telling me the insertion point is 59,381. Let's open up the world file just so we can compare those two. See, this is what it automatically read, which it's slightly different. 581, 5938, 692. Yeah, so we don't want to modify that anyway. Generally speaking, if you know your world file is in the correct place, you really just want to insert it and let it read the coordinates from the world file. That way it reads it all the way out as many decimal places. I think CAD can read out to 16 decimal places, but you just want to, let it use the world file that is downloaded with the orthophoto itself, because that's the instructions on where to place it. And then the orthophoto will come in at the correct place and at the correct size. And this is the line we drew. Now remember, this is not the top left corner of the picture of the entire image itself. This is the center of the top left pixel. So if this pixel that's the center of it, I'm just drawing perpendicular lines. and copying them down so that we can get a look at what the entire pixel looks like. And it's a good idea to go through this a couple of times, especially with a new project, just to make sure everything came in correctly, everything scaled correctly. But generally speaking, if you have the right coordinate system and the correct control, it's usually not going to be an issue. But this is just to show you and give you some background on what it is actually doing. So this is 1 pixel here. And we can actually check that this size we know that this is the X scale and this is the Y scale. So these pixels should be about 0.026. I should mention these project coordinates are in feet. So when we uploaded the project coordinates, we actually got our ortho photo back in feet. But the coordinates are relative. We could have uploaded our project control in meters and then would have gotten our project back in meters. It's just important to make sure you're using the correct coordinate systems and they're the same. So in this case, our drawing itself is set to feet. And that's what our control was based off of, and that's what our drawing is based off of. So this is in the correct place and at the correct size and using the correct units. Now we can check this pixel size. And you can see it's very small. And we have 0.02637, 0.02637. The world file itself goes way out to, I believe that's 10 decimal places. But I just wanted to check that pixel size and show you that where these numbers actually go, where those numbers, are used to actually scale the image itself. Now these skews are the same, but I'm going to show you what it's actually looking at right here. If I draw a perfectly orthographic line here, you can see there's a little difference there. So this is actually rotated just slightly. Actually, I should have drawn it from the upper left. You can see it's just slightly above that line, and it's also positive. And if I draw this straight down, it's just slightly to the right of that line, so also positive. And we can actually check this distance. I'm just putting a dimension on it so that we can see the distance easier. 0.00014, 0.000, that rounds to 14. And we can check, this one should be the same, but we'll check it just because for demonstration purposes. 0.00014. So that's a pixel size. This is actually the skew or rotation of the image itself. These are the scale. So that's actually, you can think about it as that's a pixel size. And this is remember, the center of the upper left pixel, in this case, for this world file in the CAD environment. And we're going to actually zoom into a place where we can see an actual pixel, and we'll just line that up as best we can just to kind of show you. Yep, see, hopefully that shows up clear on your screen, but that's a pixel. This is still a pretty, high resolution photo, but, if you zoom in close enough, you'll see that it is pixelated. All right, so this is it's not necessarily in the correct place, but it's in the place I want it because it's relative to my ground control and relative to the project control. And using this aerial photo, the end game for us is generally to produce an as-built survey or to pull quantities, just to say, okay, we moved this much dirt from this side of the site to the other, or we removed this much dirt from the site, or we brought this much dirt into the site. One of the outputs available for us is a DEM, a digital elevation model, or even a point cloud. It does give us rough topography, so we can actually, compare surface to surface. But for as-built purposes, the orthophoto, we use it to locate the curb lines, which you can see very clearly, the storm structures, another storm structure. That's actually an outlet structure. This is the warehouse building itself. This is concrete pavement. And we actually use this. We do survey a lot of data on the ground as well, but a lot of the actual two-dimensional planimetric drafting we end up doing directly from the orthophoto. As you can see, all of our curb lines. This is different types of asphalt, so there's a line differentiating them. So to bring it all around full circle, we actually fly the drone here in-house. I'm a licensed drone pilot. We upload the images to have the orthophoto created so that it's all stitched together and it is an actual orthophoto and corrected. Then once we download the orthophoto, to bring it into the CAD environment, we use the command map I insert, and we have it reference the world file, which is that little text file. So it's at the correct scale and at the correct location. All right. Thank you guys so much for listening to my presentation. And I hope you all have a wonderful holiday.